All right, so we resume with our study of Lewis dot with carbon dioxide as an example, as well as ammonia. And we've looked at a relatively straightforward example with carbon tetrachloride, 32 electrons, evenly distributed, and giving everything a perfect octet without any problems. All the lone pairs went to the surrounding atoms. Central atom had no problem in attaining an octet, so it was relatively easy. Ammonia was a little bit different. We did have this charge to deal with, which we accounted for in our total tally. And then we also looked at hydrogens here, where hydrogens only needed these 2 electrons rather than the 8. So again, it was a twist, but not anything that was problematic. That's not really going to be the case here with carbon dioxide, where we have to form multiple bonds. And here in ammonia, there is also not going to be a problem, but you can see here that we've actually given lone pairs to the central atom rather than the outermost atoms. So a couple of different looks at compounds. So let's get started with carbon dioxide. Carbon dioxide has CO2. The carbon being in group 4 gives us 4 valence electrons. The 2 oxygens here from group 6, each giving us 6 valence electrons for a total of 12, and that's how we arrive at the total of 16 in our bank. So we will continue with the process as we have with other examples, and next draw the skeletal structure. Carbon in the center, oxygen on either side. And by drawing this foundation, we've used 2 bonds, again at a cost of 2 electrons apiece. That's 4 electrons used just to draw the skeletal structure. So we'll make a note of that here. It means we've only got 12 electrons left. We go back to our structure. We look at the outermost atoms, which are the oxygens. They each have access to this 1 bond, therefore ownership of these 2 electrons, just as carbon would, of course, because they're being shared. So they both have rights to those 2 electrons. Given that each oxygen has 2 electrons and needs 8, that means it's missing 6. So we'll go ahead and give them 6, just as we did before. Again, now in the form of lone pairs or dots. So 6 electrons, there's 1 and 2, 3 and 4, 5 and 6. So 3 pairs, 6 electrons, 2, 4, 6, 8. Oxygen is good to go. Let's look at the one here on the right. 2 electrons from the bond, add 1 more pair here. That's 2 and 4 and 6 and 8. Now this oxygen is good to go. So I added 6 over here, 6 over here. That's a total of 12 electrons I've added to satisfy the octet of oxygen. So I'll make a note of that over here. None left. Now, we encountered this before, and it was not a problem. But that's because whenever we ran out of electrons in the previous examples, our central atom already had an octet. So running out of electrons was really not an issue. Well, here we look at the central atom now that we've satisfied the octet of the surrounding atoms, and we see carbon has 2, 4 electrons. 1 bond, 2 bonds for 4 electrons. It needs 8. It has 4. It needs 4 more. Where do we get those 4? We're out of electrons. So this is the point at which we have to form multiple bonds. We have to economize these electrons. That means we're going to have to share them. So what we're going to do is we're going to take away, let's say, this pair from this oxygen and this pair from this oxygen. And instead of them being lone pairs solely belonging to oxygen, notice 2, 4, 6. These 6 electrons are not being shared. They are non-bonding electrons. That means they're not involved in the bond. They're not being shared. They only belong to oxygen, which is okay as long as the carbon still has an octet. However, it's not okay now because the oxygen has an octet, but the carbon doesn't. So it's not really fair for this oxygen to have so many electrons all to its own when the carbon here is basically starving for electrons. So we're going to take away from one of these oxygens on either side and give to the carbon. Not necessarily give, but rather share. So let's erase these electrons here, and erase these electrons here, and go back, and rather than have them belong only to oxygen, let's have them be shared between the oxygen and the carbon. Notice how oxygen is no worse off. It has 2, 4, 6, 8. It still has an octet. But instead of these 2 electrons just serving the needs of this oxygen, these two electrons can serve the needs of both oxygen and carbon and be mutually beneficial to both. We'll do the same thing here. The electrons that were here that were just oxygens are now going to be shared between oxygen and carbon. This oxygen still has 2, 4, 6, 8, and is no worse off either. But now let's look and see what's happening to the central atom of carbon. It has 2 electrons, 4, 6, 8. Now by forming these double bonds, we've taken the same 16 electrons as before, but rather than satisfy the octet of just these two, we've been able to satisfy all 3 atoms' octets. Thereby, carbon has 2, 4, 6, 8, as does each of the oxygens, 2, 4, 6, 8. And that is why we have formed multiple bonds. Let's look at our last example here. Ammonia. So NH3, nitrogen being in group 5 gives us 5 electrons. Each oxygen in group 1 gives us 1 electron. So that's a total of 3 times 1, or 3 electrons coming from the 3 hydrogens, for a total of 8 electrons. Let's form the basic structure. Nitrogen in the middle, 1, 2, 3 bonds, and put the hydrogens around it, and we've used 3 bonds for a total of 6 electrons. So 6 are gone. That leaves us with 2 electrons. Let's see what's going on here with the hydrogens. The hydrogens need to have what? Only 2 valence electrons, no more. So how many do they each have currently? Just the 2 valence electrons from each of these bonds. So you see this bond here, that's 2 electrons worth. This one's 2 electrons worth. And so is this one. So these hydrogens actually have the 2 electrons that they need. They don't need to be given anymore. Great. Let's turn our attention to this central atom of nitrogen. Notice how it has 1 bond here from this hydrogen, and 1 here and 1 here. That's a total of 6 electrons. It needs 8, so it needs 2 more. These are the 2 we'll give it. Minus 2 electrons gives you none left, which is good. We're supposed to use them all up. And where do we put them? Right over there. Now nitrogen has 1 bond, that's 2, 4, 6, and 8. So in this case, we weren't really giving the outer electrons lone pairs, but rather the inner atom had the lone pair of electrons. So again, Lewis Dot just takes these electrons, the total electrons, distributes them in such a manner so that we have the most stable configuration, which is the configuration that gives everything an octet of electrons, whether that be 2 for hydrogen or 8 for most other elements. Alright, moving in line with, after drawing these structures, how then do we look at their 3-dimensional structure? How do we take this 2-dimensional structure and apply that to a 3-dimensional image? Well, what we use is the VSEPR model, which basically stands for electron pair repulsion. And this only uses valence shell electrons. So, of course, electrons having a charge that is negative and being in close proximity, those negative or like charges will repel one another. As they repel, they push against one another, straining the bond and basically twisting them and configuring them and contorting them into different angles and therefore shapes. So how then do we determine exactly what the geometry or the arrangement of this particular compound is? Well, the first thing is to make a distinction between what with the terms arrangement and geometry. And again, different textbooks will use different terms, but essentially one of these represents the general shape. For example, a 3-sided figure is a triangle. That's a general shape. A more specific definition or a geometry would be to tell us what type of triangle. Is it a triangle of equal sides, which would be called equilateral? Is it a triangle that contains a 90-degree bond, which means it's a right triangle? What specific kind of 3-sided figure or triangle do we have? Therefore, we're going to have a general shape and a specific shape given to each one of our compounds. So in order to find the general shape, we're going to look at the total number of electron pairs, or as we call them, domains. And so in order to do that, we just look at the total number of basically electron pairs or domains, on, again, just the central atom. So the geometry is based only on the central atom. This total amount is going to give us the general shape, the arrangement, so to speak. The specific, though, geometry or shape is going to be based on how those domains are classified. Are they bonding domains, meaning are they straight lines or bonds? Or are they non-bonding domains or pairs? Are they dots? Because if you look at them in total, that'll give you a general shape, a triangle, for example. But if you look to see exactly how many of those domains are dashes and how many of them are pairs of dots, that'll give you a more specific look at the geometry of the shape. So, to determine the electron arrangement in geometry, you'll follow these rules, which is to, first of all, draw the Lewis structure. That's why it's very important to draw it correctly. Then you look at the central atom. Again, the central atom only. Look at the total number of pairs or domains that you see, the bonding and non-bonding, the lines and the dots. And that'll give you the general arrangement. Is it linear? Is it trigonal planar? Is it tetrahedral? And so on. Then within that arrangement, within that classification of shape, what is the specific combination of dashes and dots? Are they all dashes? Are they all dots? Are there some dashes and some dots? How many of each? Specifically, how many bonding pairs or domains do we have? How many bonding pairs and how many non-bonding pairs? And that'll tell you the specific shape or geometry. So, if it's trigonal planar, is it actually plain old trigonal planar, or is it actually a bent version? Is it plain old within tetrahedral? Is it plain old tetrahedral? Is it a trigonal pyramidal shape or a bent shape within this particular arrangement? Again, it's like saying, is this a triangle? And if so, plain old triangle, X type of triangle, Y type of triangle, and so forth. And again, this is only towards the central atom. And last of all, the reason why we use the term domain here to represent pairs is because a domain represents a type of bond, if you will, or a lone pair. That in turn just simply means that a double bond and a triple bond represent one bonding pair or domain. It's one bond, it's not plural, it's a double bond, not a double bonds. So one double bond just represents 4 electrons being shared, not necessarily 2 individual electron pairs. So you should think of double or triple bonds to be the equivalent of just a single bond as far as the classification here goes. That means if you have something like water, this is the Lewis dot structure for water. This is the central atom for water, oxygen, right? It's got one bond, 2 bonds, that's 2 bonding pairs, and then it's got another pair here that's non-bonding and another pair here that's non-bonding. So overall, generally I have 1, 2, 3, 4 pairs. 4 pairs. That puts me in the total of 4 domains. So the general shape of this is tetrahedral. Specifically, however, water has 2 bonds, that's 2 bonding pairs, and specifically 2 non-bonding pairs or domains. That's a 2-2 combination. So within 4, I'm going to look for the 2-2 combo, which means that water is bent. Water then has a 105-degree bond angle as opposed to the other types of tetrahedral compounds. And therefore, what this does is it strains or pushes down on these bonds. And so the true shape of water is not so much a flat line, but rather this sort of bent configuration. And that's why you would see water written like this more so than you see on the previous page. So again, what you want to do is draw your structure, count the total number of domains. Again, double and triple mean the same as a single. So the number of domains, find the total here, get the general shape or arrangement, and then specific combinations of dashes and dots, bonding and non-bonding pairs and domains will tell you the specific shape, just like a specific type of triangle can be identified by looking at properties of that triangle, but if we were just to give it a generic classification, we'd say it's a triangle. But if we wanted to be more specific, we'd have to look at further details of that triangle. Again, this table is just one to be memorized. It's recommended that you memorize it in sections of 2 domains, 3 domains, 4 domains, and if the course allows 5 domains and 6 domains, which is going to be in most cases. And so it's important to know not only the total number of domains in the general arrangement, but also know the specific types of combinations and therefore the specific geometries and shapes that fall under or are subcategories of that arrangement. And then that will give you more information about bond angles and even further information still.